How'd the homework go? Yeah, I had a couple questions on the homework, or one question. What was odd about the homework? What was it more troubling than other homeworks? Last couple? So let's see. Here's what I did for the homework. I guess I'll just go over some of this to maybe it'll help clarify some. So the first problem, as I recall, is here you've got these data, analyze them using the matrix method. And so for the matrix method, we look and say we've got, let's see, full factorial and 3 factors, some center points. We've got our data. So one of the things we'll need would be the SSE to get S squared. And to do that, that's what this is over here. So to get SSE, we need, for each data point, we need a model prediction. So that means we got to go through all the model fitting. But once we have this model prediction, we take the difference between them and we square them, and then we add them all up, and that's SSE. And then SSE divided by n minus c would be S squared. So that's how we get S squared. Is everyone all right with that? Okay, so then how do we get, we need to get this model, this y hat. So in the matrix method, we first need to define x. So there is x right there, and I just copied it down here. So there's x. X transpose, I just kept track of how many rows and columns I had. I highlighted the right dimensionality, typed in transpose of that guy right there, and that gave me X transpose and cleaned it up with changing some column sizes. Is everyone okay with X transpose? Next thing would be to multiply this times this. So I highlighted, well, okay, what's the dimensionality that's going to work for that? And then do the matrix multiplication. Make sure to hit Control-Shift-Enter when you do that, and it populates the entire matrix instead of just one element. And we notice it's a diagonal matrix. That's great. That means it's an orthogonal design. And the inverse of this would be down here. I highlight the dimensionality, type in M inverse of this guy, and it's just 1 over each of the elements because it's diagonal, and only because it's diagonal. And that gives me X transpose X inverse. So our B vector is going to be X transpose X inverse times X transpose Y. X transpose Y is just the sum products. So next thing I need to get is X transpose Y. So matrix multiply again, the X transpose times Y. Once I have those, then, whoops, then here I multiply X transpose X inverse times X transpose Y, and that gives me the coefficients of the model, and then I've labeled them here. Is that hard to read back there? Got it? So I labeled them. This is the mean, or sorry, mean. These are the main effects, interactions, through interaction. So I got those. Next thing I need to do is to get the noise in those coefficients. So that's where I work down here. The variance of B matrix is just that X transpose X inverse matrix times the scalar SP squared. Oops. So the X transpose X inverse matrix times, oops, S squared. So if you take that times S squared, you get that. That times S, whoops, that times S squared, you get that. And then these end up being, I just did this just to pull off easily the diagonal elements in a formula. So these are just those diagonal elements, and they end up being the noise of the coefficient. And so then we can do a t statistic for each of those. B divided by the square root of the noise is the t value. And then for p value, you can just use you can use your tables in your book, or you can use the Excel function like I did. And there you have it. Now you can look at what's significant, what isn't significant. And then in our model, we had those things significant, so those things would go in our model of our y hat. All right, any questions on that?
So what does it mean when it asks, like, analyze the residuals?
Analyze the residuals would be to make the residual plots like we had.
And you want all the residual plots when you do that, or just like the ones from the significant factors?
Which part of the problem was this one? Is it? Okay, so that would be the residual plots that we have, and I can show you. Oh, I don't have them here. I've got them in a different sheet. Let me see if I have them here. So residuals versus run order, which if we don't have run order is meaningless, so that's no big deal. Residuals, the residual plots would be residual versus fitted values for the heteroscedasticity, a half normal plot of residuals, and residuals versus each factor level would be the main ones, and I'm missing one in there. Well, I did say residuals versus run order, but that's pretty meaningless in some of these because the run order isn't given to us. So then problem 2 was just do it all again, except now run 8 is missing, and the thing that we notice is, okay, it's now not orthogonal, right? We have off-diagonal elements, and so that is not as clean as the orthogonal design. And in these problems, what I've done is somewhere around here. You can also just run the regression tool to confirm what you've done with the matrix stuff, which I think is good. Yeah?
Can you figure out the variance in the coefficients if you don't have a diagonal matrix?
You still pull them off the diagonal, so it's still the good question. So next question is, how do we get the variance of these? So here we have a non-orthogonal design. These still are the variances of the coefficients, but we haven't talked about how we deal with covariances. We're not going to really get into that other than, all right, it's a bit messier when we drop variables. We have to be careful in our procedure, which is what we've just learned, on how to go about trimming our model because of that non-orthogonality. But there we have SBs, and that's one nice thing is you can say, well, if you didn't know, just say, well, those are the ones down the diagonal. If you do the linear regression, it shows you get the same ones. So that was problem 2. Problem 3, what was problem 3? I did some of this stuff on Minitab. You don't have to do it on Minitab. I was just showing here how you could do it, and I showed you if you dig around in Minitab, you can find where it will spit out the X transpose X inverse matrix for you. And then this problem was pretty straightforward, or pretty short in, if you do uncoded values, you get a non-orthogonal matrix. If you code them a certain way, you get an orthogonal matrix. That's pretty neat. If you code them a different way, you could get a non-orthogonal matrix. So this idea of coding, one of the reasons why we code values is if we do it a certain way, we can get orthogonal matrices, and then it just makes our model building and our model term reduction a lot cleaner if we're using a coded value. So, and I guess problem 3 was here we go. It was to try to mimic a fairly real situation of sometimes when you say run at -1, you don't quite run at -1. You might run at -0.98 or something like that. You get close to -1. And the question, this has come up in real situations many times, is, well, what do you put in there? Do you just leave it as -1, or do you put the 0.98 to what the real coded value is? And this problem at least shows it doesn't matter a whole lot. Right? So I worked with a guy that was pretty insistent that he would make his students, if they didn't quite get to -1, put in that 0.98 for the regression, but it doesn't really matter a whole lot. So that was the point of that, which I thought was kind of a neat problem, but I probably think these things are neater than you guys do on average. So, okay, does that help clear things up at all?
Are you going to put this, can you put this on Blackboard?
I'll have the solutions on Blackboard. I generally don't put spreadsheet solutions on Blackboard, because then I don't want those to get out there, because then they're real easy just to have the answer done. Even though I probably recognize that this is probably a little bit easier for you guys to work through than when I sort of take screenshots. But I did try to, in the solutions, I did show like this whole page, and I made comments on the side of this is orthogonal, this is not orthogonal. So that should be posted soon. Okay, so that's that. This is where we left off in the notes, and again, it's has a lot in common with what we just talked about. And this is, let's just go through our procedure for a central composite design and doing the analysis with using the regression tool. So the first step in our analysis of the design is, let's look at this. We've got a 3-factor central composite design. The thing was, we ran the thing in 2 blocks. So, that's really frustrating. So we ran it in 2 blocks, block 1 and block 2, and we have full factorial with some center points, and then we also have some star points, a few more center points after that. So let's look at going through the entire analysis of that. So look through that. This pen isn't working anymore. So first thing would be to let's regress the entire quadratic model. And you see on Excel, I've got the entire quadratic model there. This is what it looks like on Excel. So this is where I got this printout. So I've got a column for each of those things, and so to run the regression, I just go data, analysis, regression, and I put in X range. I'll say that's the full model. Y range is this guy right there. I say I've got the labels, 95% confidence intervals. Output range, I'd say put it somewhere, tell it what residuals I want, and I'm going to cancel that because I've already done it. And then it spits out this right here. Because I highlighted the labels, it gives me those nice labels instead of x variable 1, x variable 2, which you might have had. And so, first step is, there we have it, there's the full factorial, or the full quadratic model that we've put on there. And now, first step would be, well, let's look for outliers. So for outliers, I made the residual plots. Went through all the pain of making the residual plot in Excel. And so one of those boxes to check would be the residuals. So I took the residuals and made a half normal plot out of them using our formula for a half normal plot. And we look at that and say, we don't have any outliers there, so good. That's the first step. Second step would be to look at reducing the model. So when we have a block design, when we look at model reduction, first thing that we look at was blocking needed. And here, what do you think? Did we need to do the blocking or not? Doesn't look like it. So you look at those guys right there, p-value is pretty high, t-value is not so big. So it looks like the block effect wasn't really needed, so we could remove it. And how do you do that in Excel? Well, you just take and instead of, I guess I didn't highlight initially when I did this. When I first highlighted, I would have had to highlight the blocks to include the block variable. Next time, if I want to remove the blocks, I'd run the regression again, but I would not highlight the block column. So everyone got that? Understand that? So that's this block removed. I just made a new sheet in which I deleted the block column, and I highlighted that, and I regressed it again. So now the blocks are gone, and we have one more degree of freedom added into the noise. So the block effect is now into the noise. So before we had 9 degrees of freedom in the noise, mean square was 68.9. Now we have 10, and mean square, which is s squared, went up a little bit, but not a whole lot. So now we've got the full quadratic model right there with the block removed. The next step in our model reduction procedure would be, let's look at now each variable in its entirety in all its terms. So let's start with variable A. Do we need A as a variable, or should we do the test to remove it? So we look at A and say, well, the main effect of A is really big, and so we could stop there. AB is not so big, not so big. That's just marginally significant. But because we have a really significant term with A, we're going to say, all right, we can't remove all of A in the model. We could test it, but with that huge main effect, the test is going to come back. You can't take all of A out of the model. Does that make sense? So we go to B. So on B, same sort of thing. There's a big effect, the main effect of B. There's a fairly good B squared. So certainly we can't remove all of B's terms in the model. Then we look at C and we say, all right, C has maybe that doesn't look to be too significant. That is non-significant. Same with that one. And that one. So we look at all the terms that have C in them and say those don't really look too important, right? They all are insignificant. So let's drop C from the model. And again, so we're dropping 1, 2, 3, 4 terms. And so our SSE, how much do we figure that's going to go up by? If C is doing nothing, this should go up by 4 times this, right? So how do we do that? Again, what I've done, I copied all this over. Essentially, you delete that column, that one, and that one, which I've done here. So I've deleted all those C columns, ran the regression again. SSE did go up. It went from 765 to 906. And our test then, did it go up too much? So we need to figure out what's the noise or the variance explained by the drop terms, which is how much did SSE increase? And so you see what I've done is I've taken this value right here, and that value there, the difference between those two, SSE increased by 141.8 when we drop those terms. And how many terms we drop? 4. We divide those two, we get 35.3. So that's the variance explained by the drop terms. And we're going to compare it to the variance of the full model, which was that guy right there, or that squared, either way. But the mean squared error, or residual, is the S squared. So that divided by that ends up being 0.46, which is real small. And so I just want to make sure that is the same example, right? Yeah. So ends up being 0.46. Our F star has 4 degrees of freedom in the numerator, and 10 degrees of freedom, I got that from the full model, or the larger model. So the 10 degrees of freedom was right there. So, was it okay to drop C in all of its terms? Yes, good. So we've done that step in model reduction. So that was 3A. 3B is then, now let's look at individual terms. So we look at all these terms in the model, and we say, this one right here is the most insignificant. It's the only one that's insignificant. So we're going to drop it from the model, which means we're going to take that, delete that column, which is right here. So got some nice coloring here, but that comes later. So I did that, ran the regression again. This time, all the p-values are significant. So now here we have A model, A, B, and the quadratic terms. So the main effects of A and B and their quadratic terms. This kind of leads us to believe that we're very close to the optimum location where we have these, well, I'll take that back. We still have some significant main effect terms there. But in the region of significant curvature. So that's where we're at now. We've got our model. Now we need to test the model for model adequacy, which means we're going to need to do some residual plots, but we're also going to need to do this lack of fit test. So the lack of fit test is a little bit trickier here, because now when we've got our reduced model, our lack of fit test says we're going to do two things here. We're going to get S squared from the places where we have replicates. And everywhere we have replicates, we're going to calculate S squareds, and we're going to pool all those together into one S squared of pure error, which is from replicates. Then once we have that, we're going to find the S squared of everything else. Remember, all the other places without replicates. And we're going to compare those two. And we call that latter one was called the lack of fit, S squared of lack of fit. And I don't know if it's easier for me to do it off here or not. Not a whole lot different. So what I did is I looked through here and said, all right, I'm going to try to identify where we have replicates. And the color coding is kind of nice. You guys, we're looking for like a pizza party today, but we do have color-coded spreadsheets, which is like it's a close second. It's kind of nice. So we have, this green one and this green one, those are replicates, right? So we have 17 and we have 7. So I can take those and I can get an S squared. And then these purpley ones are like 44 and 55. So I can get replicates at the corners, at these corner points from those various colors. And then I have these two chunks of center points. So I can get center points. I can find the SSE, the degrees of freedom. I can pull all those together and get an S squared of pure error from that. Does everyone see how that worked? So all of this down here represents, this is all the S squared from replicates. And I get all that into 1, and so I have 11 degrees of freedom from my replicates, and it gives me that S squared. So then I need to compare it with the S squared of everything else. And so the easiest way to get that is by subtraction, if you will. This, the total, I got from the regression. So that's 952 right there, and 15 degrees of freedom right there. That's where I got those two things. I can't use the pen right now unless I reboot, so I'm trying to do it a different way. So then, by subtraction, the sum of squares partitioned, so I've got the total minus what I did for pure error. That's all the stuff that's left over. The degrees of freedom, also that minus that. And I take the ratio of SSE divided by degrees of freedom, which gives me the variance in the lack of fit. So now the F test is just the ratio of S squared lack of fit divided by the variance calculated from pure error. And if it's a good model, those two things should be the same. If it's a bad model, then the lack of fit should be inflated, which it is. It's quite large. The critical value for F, keep track of our degrees of freedom there. And that gives me 10.6 compared to F critical is 3.5. So we would reject the null hypothesis that the model's okay and say this model shows significant lack of fit. So for us, we would say, all right, we're not done. We need to go back, figure out why this model doesn't fit. What happened? So do we need an extra term? But just for sake of completeness, I think I did plot residuals, and obviously the easiest way to do this is I did the same analysis on Minitab because it just, with a few clicks, we'll do a lot analysis, and I pulled the residuals plots from that. Residuals versus run order. If this run order is real, we have a problem there. Does everyone see that? We have a downward trend where we have things decreasing with time. So hopefully we've randomized our run order to help with that. We look at the residuals versus fitted values, and we're wondering if we have heteroscedasticity here. We're about almost an order of magnitude in our y values. So that could be happening here. The fix for that would be a transformation of data, so ln of y instead of y, and that may help lots of things. So if this was a real situation, I would be looking at, well, let's look at a transformation of the response to see if that stabilizes things. We might come up with a different model that doesn't show lack of fit, all those sorts of good things. Maybe have outliers, not exactly sure. That's fairly close there. And then residuals versus factor level A. We're just looking, are they centered about the mean here? Not too bad. This one, these look a little bit low right here to say they're centered about the mean. That one got a little high. So possibly we're missing some sort of term in B to reach down and model at the +1 side. So we have some serious problems with the model, and we would need to fix them. But I went on to say, you know, if the model was okay, then we would make a contour plot. And so contour plot is you take factor A and factor B, and then these are y values, right? 80, 40. So we could say if we're trying to maximize it, we'd be over here. If we're trying to minimize it, we'd be down here. And what do those dots represent? What do you think those are on there? Good, data points. Those are data points, right? They correspond to -1, +1, zeros, and alphas. And it's really to put them on, really important to put them on for essential composite design because of this, because very often where we want to be happens in the corners of our diagram. And notice if we say run here, we are extrapolating our model, right? So our model's good in the region we took data. It's good in this circle. So if we're running out here, we're doing some mild bit of extrapolation. I mean, maybe the model will still hold reasonably well. Maybe it's worth a try. But in our general procedure is we don't extrapolate our models, especially these quadratic models. So we'd be really nervous about telling anyone or predicting some value out here without at least running a few data points out there. Okay, any questions? That's sort of the run through of the whole procedure of analyzing response surface method designs. Okay, so that finishes one huge chunk of the class. So in the class we have basically two big parts. The first part was taking you from I know mean and I've kind of done the standard deviation all the way through propagation of error, linear combination of random variables, confidence intervals, hypothesis testing. That was sort of the very basic level statistics. Then this next chunk was all this design of experiments, which I think is really important stuff. This is the stuff that not a lot of engineers know, but the ones that do know it well can really impress and do very well in their positions. Any sort of job that has quality in the name is using these techniques. Quality control, quality assurance, Six Sigma, Lean Six Sigma. Anyone heard these sorts of terms when you're out there looking at internships? Okay, good. An electrical engineer. Okay, and it's fairly common, I would say, when I talk to students who've come back from internships, talked about 3 or 4 of them just the start of the semester, who they ran into, okay, I was in some sort of quality assurance, quality control group, and they were doing all this sort of stuff. So we got to this point, and then now you can do the projects and you can apply this. So I'd encourage you, try to apply these techniques when you're doing your labs in subsequent courses. It takes a lot of really hammering at this stuff to really get it. So I think I took 3 graduate level statistics courses, and even at the end of those, it still took me a while till I thought I really had a good handle on the stuff. So this is your first of many courses, of many encounters with statistical design of experiments. Some of you probably are looking to leave it behind, but others of you may not. So okay, so these are 2-level designs, and this gives you the tools to handle a lot of problems, a whole lot of problems. And what we're going to do for the rest of the class, though, is just look at one extra situation and a very common analysis technique that I'd like you to be familiar with, which is analysis of variances. So, whoops, keep going to the wrong place. So we're going to go, for the remainder of the class, we're going to talk a little bit about Chapter 9 stuff. So now we're going back into the text and looking at Chapter 9. And this is where your author deals with analysis of variances. He also covers 2-level designs. So in about 1 or 2 sections, everything we've done since Chapter 6, he sort of crams into there, which I don't think quite does justice to the material. Okay. Let me move this up. So we've done 2-level designs, so 2 to the k designs or 2 to the k minus something designs, but the whole time they've been 2-level, which means for each factor we have a low level and we have a high level. You know, later on we add center points and star points and that kind of stuff. But very often the situation arises where you have a factor in which just naturally it has more than 2 levels. So some of you had this in your projects. So any group remember when you said, oh, I had a certain factor and I said, okay, that's more of an ANOVA or that's sort of like 4 levels of one factor. What groups had that happen? I'm asking you for these examples. Must be the groups. No. Must be the groups that are gone today. Or none of us remember. Okay. But I remember saying it a few times in your project meetings that you may have had one factor that was really several levels of a certain factor. So, so some of the examples here would be if you have, you know, four brands of something, or four suppliers. There you have four levels of the thing. So I think one of these things was 4 brands of flux when you're soldering. And so you have 4 brands. It's not really like a 2 level with the center point or anything. You have just 4 separate categories of things. So 4 levels of one factor. So how do we analyze that? And there's a fairly creative, sort of inventive test that someone did, and we're going to get to that now. So first all, some definitions. And again, you have, since we've already done this 2-level designs, you have seen these definitions. The only one that's, say, a little bit, we're going to call each, so if you have a factor, it may have 4 or 5 levels. Each level is called a treatment. So you think, okay, I did something to this thing, it's called a treatment. Okay, let's not worry about fixed effects or random effects model. That's, the analysis is the same for those, and completely randomized experiments and so forth. So I was so excited several years ago when I would teach ANOVA routinely that I came across this great explanation of ANOVA in a different text, and so I took it and put it here, and then tweaked it a little bit, and I think it made it better. And so this is probably the most exciting explanation of ANOVA you will ever come across. So with that intro, setting the bar pretty high. So kind of like when they made Star Wars 1, you know, the bar was set really high, but it didn't quite fit. So, all right. So I'm going to try to avoid some sort of Jar Jar Binks moment in class. So here's what we have. We have done some experiment, and so it'd be great if it was a little bit more definitive on what we did. But we took and measured, here we go. We had 9 treatments. So you can think of these as 9 brands of something, right? So we have 9 treatments, 1 through 9. And for each of those, we did 9 replicates. All right. So we did 9 replicates. So for treatment 1, we did 9 repeats. We can calculate an average of those replicates and a standard deviation of the 9 replicates. Is everyone with me? So we did that for treatment 1. We did it again for treatment 2, 3, 4, 5, 6, 7, 8, 9. And, which is kind of fun, we got box plots. Box plots are great. So we can make a box plot of all these guys, right? So these are box plots of all 9 of those, each treatment, all 9 of them. And what do you think? Do you think there's a difference between those different treatments? So the different brands of things? Do they look like they're very different? Do they look like they're located differently? Yes? Okay. They don't look too terribly different. Remember our box plot slippage tests? Remember those? Chapter 5-ish? Those rules? Okay. Those rules would kind of say that there really isn't a whole lot of difference between their means. But anyway, so that's those 9. But then if we look at this, now this is where you got to hang with me, is if I take these averages of the 9 treatments and I make a box plot of those. So I've got 9 numbers there and I make a box plot of those. That's what this guy is right here. So obviously it's centered about where all the other ones are centered about. But what do you notice about that particular one compared to the other ones? It's smaller, right? Does that make sense that it's smaller? what really super important statistical theorem would tell us that it should be smaller? Very good. So the central limit theorem would say that what we're looking at there, those are 9 means, right? So we're looking at some sigma of x bar. That's the noise in that guy, right? And that's equal to the noise of the individual measurements divided by n. Only I'm not going to call it n, I'm going to call it j. The replicates here are j replicates, and then the number of treatments is I. All right. So that's super important. And so j here is 9. We have 9 replicates in each mean, and when we have all those means, we have this thing shrink. Right? Okay, so that works. And that happens when all the means are the same and it makes sense to average them together. So now let's look at this same situation in which we come through here and we say, if we keep all this the same, the noise level is the same, but one thing that's different here is now the treatment means are doing something. Right? The different treatment means are affecting our response somehow. And so now our box plot would look something like that. So here are the treatment means. So notice now, this one's a lot higher than this one, and this, they're all different, right? But the noise in each of them is exactly the same. The noise in each box. So these guys, the standard deviation of, say, these numbers is the same here, 2.74, as it was up here, 2.74. Okay, so now when we go and say, all right, let's take these 9 numbers and let's plot that box plot, we get something that looks like this. So now it's not smaller, but it's bigger, right? And the reason why that's bigger is because these means are different from each other, right? Because this box plot represents this mean, and this mean, and this mean, and this one, all lumped together into one box plot. Okay, so that means the central limit theorem didn't really work for us, if you will, because the means weren't the same. So now this is where someone figured out a really neat way of doing a statistical test. So what we're really wondering then, when we're doing an experiment, we're wondering, do we have a situation like this, where all the treatments are the same, or a situation like this where, hey, there is an effect of the treatments. They are changing the mean of this stuff. So the test we could do would be, keep wanting to pull this thing out, would be, we can calculate S 2 ways. S, the individual measurements. I could take these 9 numbers right there. If I take their standard deviation, that's sigma x bar, right? Or S x bar. And I could back out, if I know a number for this guy, and I know J, I could calculate this, right? And that is the noise of the individual measurements. So that's one way I could get it. I could get it from these numbers right there. And then I could get that same number by pooling all these together. Each one of these represents the noise of the individual measurements, and we're assuming they're the same at all the levels. So I could take all those and I could pool those things together into a standard deviation. Is everyone okay with that? If all the treatment means are the same, which is if we have this happening, then the standard deviation of individual measurements that we get from the means, that we back out of this, that value should be the same as these values. Does everyone buy that? So if the treatment means are the same, those things should be the same. And if now we're thinking, okay, we've got 2 standard deviations, which is like 2 variances. We're thinking f-test for that. But on the other hand, if we do the same set, or the same analysis for this data set, and so if I take those 9 numbers and I calculate S of x bar, and then from that I get the noise in individual measurements, if I do the same thing here, what's going to happen? The number I calculate this way is going to be bigger or less than the number I get by pooling these together. It's going to be bigger. Good. It's going to be bigger simply because the means are different. So that is inherently the test in ANOVA. That's what analysis of variance does. It says calculate the variance 2 ways. One, from your treatment means, and so back it out, and again, it's the variance of your individual measurements. You're just sort of backing it out by calculating the S or S squared of x bar and then multiplying it by j. So you get it that way, and then you compare it to the noise you get from pooling all these together. And notice these ones circled in red, these estimates of the variance don't depend on the location of the mean, right? So if this box is up here or down here, it's not going to change that number because it's each data point minus that mean. So it doesn't matter if it's up here or down there. But the number I get here does depend on whether these things are up there or down there. So this one, I'll try to do blue. So this way of calculating the variance of individual measurements, it depends on where the means are located. If they're all located the same, then we'll get a good estimate of it. If they're not, then we'll get an inflated estimate. This one circled in red, by pooling all those estimates together, that one is insensitive to the assumption that the means are the same. Okay. So, pretty exciting explanation of variance, or was it a bit of a letdown?
I'd say it's the most exciting I've ever heard.
The most exciting ever heard? That was diplomatic of you. Also, good. All right. The least exciting you've ever heard as well? That would be the next question. All right, so let's do this. So let's do this group problem. Look at these data. Calculate S squared those 2 ways. And then do the f-tests. So use those numbers for, let's do that first. Take those averages and back out the variance of individual measurements from them. While you're doing that, I'm going to try to restart this thing. All right, so I'm not going to do that. Thanks. I'm just going to leave that up there. Hold on. I'll try to print it. I'll print this out. Maybe it'll happen quickly. How many people are here? Someone do a quick count for me. How many people are here? Please count. What's that? How many? Thank you. 24. Okay. Whoops. I did it. All right, we'll have one extra. Kurt. Okay. Okay. So, All right, you guys start working on that. I'm going to get that critical page of notes for some of you, unless half of you want to look on Chris's page and half on Katie's, or Lizzie, whoever it was. Okay. Okay, if you guys want to start passing these around here. If you want to pass those around, Derek, please. Thanks. Oh, I can't really reboot this. Okay, anybody get say a standard deviation or a variance of those 9 numbers? What'd you get? 107.37, anybody get that? Oh, you got a different number? You have different numbers than these? Oh, that's good. Oh, I printed off this next one? All right, we'll do that one then. We'll just do them in different order. Pardon?
Is that the square value?
That's s squared of x bar.
But I got that, I just got that.
Pardon?
That's what I got for just that's not six.
Oh, of x bar or x? Okay. Is that what you got then? Okay. Let's do this. So s squared of x, that squared times something. Oh, yes. Okay, an important thing. So this 10.36 is, I did get that too, I just didn't see the squared. So this 10.36 is the standard deviation of these 9 numbers. These 9 numbers are averages, right? So this would be S of x bar. Is everyone okay with that? But that's not what we really want for the test. We want to use this to back out the noise of the individual measurements. So the central limit theorem says how these two relate is by, well, how the standard deviations relate is by the square root of n. So the variance of the individual measurements would be the variance of the mean, which is this 10.36 squared, times how many data points went into each average. So how many data points went into each average here? 9. So that's these 9 right here, these 9 observations, not the 9 treatments. So where am I? So 966-ish. Everyone okay with that? Okay, so now the next step would be let's calculate variance another way. We have,
wait, so it's 10.36 squared times 9?
yes, right? So we're used to seeing the central limit theorem as s of x squared is this number here divided by the square root of 9. We're just rearranging it. So I'm using, where is it? I'm using the central limit theorem. Sigma of x bar equals sigma of x divided by the square root of n. And I'm just solving for that guy. Okay. So now, change colors again. So now we have another variance, or another estimate. We have 9 other estimates of that same variance, and we're going to pool them together, right? So we're going to use our SP squared formula. So sum variance is going to be, so here we have 7.5 times what? What do we use to weight for our pooled variance? Degrees of freedom. In this case, 8. They're all 8 plus 8.5 times 8. On and on and on, divided by what? It's 9, 7. There we go. So again, this is an estimate of the same thing, calculated a different way. Yeah, so each of these has 8 degrees of freedom in it, and there's 9 of them. So 8 plus 8 plus 8 plus 8, all 9 of those 8s.
So, and the 72 is just 8 times the 8?
8 times 9. So it's I minus 1 times j. So, or I times j minus 1, I should say. Does that make sense?
And so if one of those wasn't the same, how would you calculate that function?
So if this one had 1 less, yeah, if this had 8 data points, then this 10.9 would be times 7, and then this would be 71.
The denominator would still be 72?
No, then this would be 71. It's adding all the degrees of freedom that are in these weighting factors. Anybody get a number for that one? Pardon? 9.62. Whole lot different. So then our F test is going to be the ratio of those two guys, right? So there we have an estimate of the variance based on the means. There we have it that's independent of where the means are located. And it's about 10.
How do you decide which one you want on the top of the
It's about 100. It's about 100. Pardon? Oh. Okay, we'll get into the steps. That's a great question of how do you decide which is which. We'll get into I'll state our hypothesis in a minute. So taking it a bit backwards here. But this one is 100 times the other one, right? So why is that one so big? Think about how we calculated it. Why would this one be much bigger? Yes, exactly. Because the means are different, it inflates the first calculation. So back to Aiden's question then, our null hypothesis is going to be all these means are the same, and our alternative hypothesis is going to be there are at least 2 of them that are different. There could be more, it's at least 2 are different. So if all these are the same is true, that means this first way we calculated variance will match the second way we calculated variance. If it's false, we'll get what we got here, in that the first way we calculated variance, which comes about from our means, we backed it out using the central limit theorem, that's going to be inflated, and therefore we'll know at least 2 of the means are different. There could be a lot more, but all we could really say is at least 2 are different, which if there are 2 that are significantly different, that can inflate this enough. So this is one nice thing about this, it gets around the multiple testing problem, right? If we were to, let's go, I guess I'll stay on here, and I'll just erase some of the stuff. So in one test, we've determined at least 2 means are different. So think about if we try to do a bunch of t-tests on the various treatment levels, right? We would have a lot of different tests to do, right? That many of them? What is that, 36? 36 tests, 9 times 8 divided by 2. So we'd have 36 individual t-tests. We'd have that alpha error problem. So the probability of committing at least 1 alpha error would be 1 minus 0.95 to the 36th power. So it's going to be fairly high. So this neat little test is one single test. We get around the multiple testing problem, and it tells us either all those means are, it tells us that I'll say it sort of clunkily, all those means are the same. Obviously, we haven't proven the null hypothesis, but all the means are the same, or at least two of them differ. And then once we go past here, once we get this result like this that say at least two of them differ, then we can explore further, well, which ones are different from which other ones. But this is the analysis of variance test. So I'm going to let you out 5 minutes early because it's Thanksgiving. Isn't that generous?